last time, we computed that the fundamental group of a sphere is trivial, at least in dimensions at least 2. And the topic for today is the one-dimensional sphere, or the circle. And we'll prove that in this case, the fundamental group is isomorphic to Z. So roughly, let me first say why you might believe this. Well, so the Z is corresponding to, so you have a loop here that winds once around, and we'll see that generates the fundamental group. And if you concatenate this loop some number of times, that corresponds to winding around the sphere some number of times. So this Z is essentially the winding number of a loop. Okay, so the main tool for the proof of this theorem is a technique called path lifting. So we're going to be looking at maps into the circle and also maps into the real line. So let P denote the usual map, the exponential map, like this, viewing the circle as sitting inside the complex numbers. Right, so the main proposition, which we'll call the path lifting proposition, is that for any based loop, so let's say loop which is based at the base point 1, there exists a unique map f tilde, which is going to be a path in R with the properties that, first of all, f tilde sends 0 to 0, and the second condition is that if we compose f tilde with the projection, we just get the map F. So this second condition can be conveniently described with a diagram like this. So we have F, P, and F tilde, and we want this diagram to commute. So, okay. So this is the path lifting statement. It says that given any loop downstairs, you can lift it to a path which starts at 0. So let's see some examples of this. So let's consider first f of t is e to the 2 pi I t. Well, so this is a path that just goes once around the circle. And a lift of it is, well, so here a lift f tilde of t. Oh, right. So let me just say we call f tilde a lift of f. So we could take f tilde of t to just be t. So upstairs, we just have the path that starts at 0, as we want to be the case, and then just travels to 1 at unit speed, and that maps exactly to this path. A couple more examples. If instead we consider the path that travels around the circle counterclockwise, or clockwise rather. So now we're gonna go the other way around. So a lift of this path is the map f of t is minus t. So here we start at 0 and we travel to -1. Another example. Let's now consider a path which is piecewise. It's given by 4 pi I t for t between 0 and 1/2, and 8 pi I minus 8 pi I t for t between 1/2 and 1. Right, so on the circle, what does this path do? So so on the interval from 0 to 1/2, this, well, it goes exactly once around the circle. So we're doing the original path here at twice the speed in half the time. And okay, but that's only the first half of the path. So then on the second interval, we're going backwards at 4 times the speed. And for half of the time. Let's see. So how many times does this go around? Right, so at time 1/2, this is e to the minus 4 pi I t, or pi I, and then we go to e to the minus 8 pi I. So right, so we go backwards twice around. Okay. So pictorially, okay, so now the lift. So let me draw f tilde. And maybe I won't write a formula for it, but well, okay, you could. How does the lift look? So first we do we do this red piece, which is lifting similar to the first example, and then we go in the reverse direction, like this. Okay, so this is a picture of f tilde, the image of f tilde. Yeah, so I guess we could write down a formula here. F tilde of t, it's on the interval from 0 to 1/2, we do 2t. So that takes us from 0 to 1. And then we do on the interval 1/2 to 1, we do, okay, so I have to be a little careful. So we should be doing minus 4t, I guess. And we're supposed to start at 1. 1 minus 4t. So at time 1/2, no. Sorry, I should have written this in my notes. But let's see if we can get it right. So at time 1/2, this is minus 2. So I guess it looks like I should put 5 here so that at time 1/2 we're at 1. And then at time 1, no, this doesn't look right. What am I doing weird here? Oh, 2. No, so I should have said 3. Sorry, I'm bad at math. I'm sorry. If I put a 3 here, then at time 1/2, this is 1, and then at time 1, it's -1. Okay. Whew. Okay, one more example. And let me just do this one pictorially, since I can't do arithmetic right now. But also this illustrates how this path lifting should work. So I'm going to draw a path. It might, do something weird. It comes and then it backtracks and then it keeps going and then it travels and then comes back around like this. So I'm drawing it sort of in the plane, but of course you're supposed to imagine this is projected onto the circle. Just drawing it like this so you can actually see what's going on. So if we were to lift this, well, to lift it, you kind of just follow your nose. And actually I didn't need to draw all of this because the lift is all gonna live between 0 and 1. So you lift, you have to start at 0, the path, and then you just kind of follow along. So it's supposed to go and then it's supposed to come back and then it does some turning back and then going forward. And then I guess it looks like it just turns back once more and then it comes all the way back and then it ends here. Okay. Okay, so hopefully you have some sense for how this path lifting works. We're going to prove the path lifting lemma next time. Let me just give some remarks about this. So we could also well, let me say it this way. So if f tilde is a lift of f with f tilde of 0 is 0. So being a lift, I guess I should say being a lift is simply this condition that this diagram commutes. That's like saying for every point downstairs in the path, the value of the lift should be in the pre-image. That's what this equation says. And that's sort of what's behind this example here. But a given, there might be multiple lifts in general, might be multiple f tilde which have this property. But the uniqueness here really comes from the fact that f of 0 is 0. So the remark is that if f tilde is a lift of f with which sends 0 to 0, so then f double tilde of t is f tilde of t plus n is also a lift of f, but with, so f double tilde doesn't send 0 to 0, it sends 0 to n. Okay, so it's also a lift because the map P is periodic. That is e to the 2 pi it plus, let me say it this way, 2 pi I t plus k is e to the 2 pi I t for k in Z. Okay. All right. So that's the first remark. Second remark. Right. So, well, first a question. So what can we say about the endpoint of f tilde. So f tilde is a path. In general, from these examples, we see f tilde is not a loop. So f is a loop, but the lift is not a loop, it's just a path. Although I guess in this example, we do see that we have a loop since we come back to where we started. But what you see in each of these is that the endpoint of f tilde is always an integer. Here it's 1, -1, here also -1, and here it's 0. And we can see that generally just from the fact that f tilde is a lift. So we know that p of f tilde of 1, this is supposed to be f of 1. That's what it means to be a lift, which is to say that f tilde of 1 is in the preimage of, f of 1 is 1. So here this is 1 in the interval 0, 1, and this is here 1 in the circle. Right, so p of f tilde of 1 is 1 means that f tilde of 1 is in the preimage of 1, which is exactly z. Okay, so f tilde of 1 is always, so the path always ends at an integer point on the real line. Okay, and this integer is like roughly how you want to think about the winding number of the path. So what we want to do right, so f goes to f tilde of 1 is like the winding number of the loop f. So here, this is some integer. So, I mean, you should see this in the examples. Here we wind once around, here we wind once in the counter or clockwise. So it's winding number with sign. Here we go once around counterclockwise, but then we go twice around clockwise. So the net effect of that is going, is -1. We go once clockwise. And here the net effect is 0, so there's no winding here. Up to homotopy, you can imagine homotoping this map, that this map can be deformed to a constant. Okay. So what we want to do with this, is show that this map defines well, ultimately an isomorphism from the fundamental, on the level of homotopy classes, so from the fundamental group to Z. Okay, so the first thing to show is that this map is well defined on homotopy classes. That is to say, if F is homotopic to G, then their lifts have the same endpoint. Let me see. Okay, let me put this here. Oh, it doesn't fit. Okay, never mind. Right, so let me explain briefly why this is true. So the idea is, well, given a homotopy, which I'm going to write like this, of loops based at 1, so these are loops in S1, we can lift to get a homotopy. Well, each of these is a loop based at S1, so we can lift each of them individually. And what we get is a homotopy of paths in R. So you just get this family of paths in R with the property that P composed with Ft tilde is just Ft, the loop that we start with. So then, well, Ft tilde of 1, the endpoint of this is again in Z for the same reason as before, since these are, we're lifting loops. But then by continuity, so we have, as T varies, we get some path in the integers, but the integers, in the integers with the discrete topology, the topology in R, but this space, there's no non-trivial paths. So by continuity, Ft tilde of 1 is constant because Z is discrete. So then this means at time 1, at the endpoints in particular, the two loops at the ends of the homotopy lift to the same endpoint, which is exactly the kind of thing we wanted. So if F and G are homotopic, there's some homotopy between them, and this argument shows that F and G have the same endpoint. Okay. All right, so now let's state the computation of, so we come to this theorem, which says that, so now we have a map like this, which is well defined. Let me call it phi, which sends a homotopy class F to the lift of F evaluated at 1. Okay, so this is we have this map. It's what we just showed is that it's well defined, independent of the representative that you choose for a homotopy class. And so the theorem is that this is a group isomorphism. So first, so we'll prove this. There are several things we need to prove. So first, we should prove that it's even a group homomorphism, and then we'll show that it's injective and surjective. So let's start with homomorphism. So we want to show that if we concatenate two paths, lift, and take the endpoint, then this is the same as the endpoint of the lift of one plus the endpoint of the lift of the other. So this is what we want to show. So the main thing to observe is that the lift of the concatenation is equal to a concatenation of sorts. So let me write down the formula and then explain it. So we do the lift of F, and then we concatenate with a lift of G, where so G double tilde is the lift of G that starts at 0 shifted by F tilde of 1. So this is the picture to keep in mind is exactly this one, where we lifted a concatenation. And you see that, well, right, so the notation is bad now. You should think of this as F and this is G. So the lift, maybe I'll draw it in red, F. So first we lift F, and then we lift, right, so the lift of the concatenation consists of first the lift of F, and then it's a lift of G that starts at the endpoints of the lift of F. And so that's the lift of G that's shifted as pointed out here. Okay. Right, so then, given this fact, so then, well, the endpoint of this full path is just wherever this second path ends. So that's G double tilde of 1, which is, so we just evaluate, this is G tilde of 1 plus F tilde of 1, which is exactly what we wanted. Okay, good. So this shows that this capital phi is a homomorphism. And now there's not so much, so the next two steps are not so bad. So surjective. So what do we need to show here? We need to produce a loop in the circle so that when we lift, we get an arbitrary integer. So I can just write down a general formula that does that. If we take fk of t to be this path, this is exactly the path that winds around k times. So like f squared is like this. K times, I guess, well, yeah. And yeah, so here, so this f tilde has fk tilde of 1. Well, let me just first say fk tilde is the map kt. And so the endpoint of this is exactly k. Okay, so that's surjectivity. Now injectivity, this is the last part. And then we conclude that phi is a isomorphism. So for injectivity, we just need to show that the only thing that maps to 0 is the constant loop, the identity element of the group. So suppose f tilde of 0 of 1 is 0. And what we want to do is that show that f is homotopic to a constant. Okay, so we're in the situation of this example here. We have some loop f, and when we lift it, we get the endpoint is just 0. We come back to 0. And we want to show that f is homotopic to a constant. Okay, well, so the thing is, so note that f tilde is a loop in R based at 0. And we know, well, we know that the fundamental group of R is trivial. So any loop is homotopic to the constant loop in R. So we can choose a homotopy. Let's say, I'm going to write it this way, f tilde sub t from f tilde to the constant 0. So the loop that's, or the loop that's constant at 0. So then, right, we can just project this homotopy. So P compose f tilde of t. Let's define that to be, so, sorry, so let me say it this way. So now define we're trying to get a homotopy downstairs on the circle. We have a homotopy between the lift of f and the constant upstairs in R. So now define ft to be the projection. So this is a homotopy between, well, P compose f tilde of 0, which is P compose f tilde, which is f, and well, P compose f tilde of 1, this is just the constant map at 0, and then P of 1 is 1. So the projection of the constant loop is just a constant loop downstairs. Okay, so this is exactly what we wanted. We showed that f is homotopic to a constant. Okay, so that's the proof, and so this is modulo proving the path lifting proposition, which we'll discuss next time. Okay, so now I want to talk about something a little different. Induced maps. So let's start with just some map between topological spaces, and let's fix a base point P and X, and let's set Q to be the image under phi. So then we define the induced map, which is a map, okay, we'll denote it phi lower star from the fundamental group of X based at P to the fundamental group of Y based at Q. And the way this map works is we send a homotopy class F to the homotopy class of phi composed with F. So the picture is, here we have some space X and some other space Y. And we given some path or loop in F based at the base point P. Well, if we just look at the image of this under phi, we just compose this picture with phi, then we get a loop based at Q. So here's phi composed with F. Right, so the main, well, right, so far what I've defined is a map, and actually it's not clear that this is actually even a map yet, that this is well defined. So let me just state that. That's an easy exercise. This is well defined. That is to say, if F is homotopic to G, then phi compose F is homotopic to phi compose G, and that's easy to prove. So exercise. And phi star is a homomorphism. Right, so since the fundamental group is a group, we want this induced map to be a homomorphism of groups. So let me explain this. So what we need to show is that, well, right, so let's look at phi star of a product of two loops, F times G. And ultimately, we want to say this is phi star of F times phi star of G. All right, so let's see what we can say. So first of all, let's just use the definition of the product in the fundamental group. So the product of two loops is their concatenation. And now let's use the definition of phi. So phi is, we just compose this concatenation with phi. And okay, so now we have to think a little bit. So the concatenation, remember how this works. Concatenation at time t, so then we do F at some, like F of 2t and G of 2t minus 1, I think, for some time interval, another time interval. If we compose this with phi, then, well, we're just composing with phi. So this is phi of this and phi of this. And so what we see is that this is exactly phi compose F, concatenate phi compose G at time t. Okay, so we have this equality of loops. But then, okay, so this is, right, so now we've basically won. So here, this is concatenation in Y, in the codomain. And then we can break this up as phi compose F times phi compose G. And then, well, now we've reached the last step, because this is exactly how phi star is defined. So we have this last equality. Okay, so the induced map is quite useful, as we'll see eventually. Let me just give you a little example. Let's take phi to be the map from the circle to itself that squares given by squaring. So phi e to the I theta is e to the 2I theta. And let's compute the induced map. So right, so to compute the induced map, so let me just remind you of what we did in the first part of the lecture. So we described the fundamental group of the circle as isomorphic to Z, and it's generated by a loop that just goes once around, e to the 2 pi I t, like this. This is the loop that corresponds to generator 1, if you think about what we said. So to determine phi star, the induced map, well, if you want to determine a homomorphism of groups, it's enough to know the value on generators. So we just need to compute phi star of f. So this is the loop. Well, yeah. So this is the homotopy class of phi of f. And well, we just want to see, well, let's say it this way. So let's just see what this loop is. So phi of f of t, this is phi of f is e to the 2 pi I t, and then phi is squaring. So this is e to the 4 pi I t. And this corresponds to the element 2 in Z. So this is F, concatenate with F. So that is to say that under this homomorphism, 1 goes to 2. So phi star is multiplication by 2, which I guess is not surprising. So phi is multiplication by 2 on the circle, squaring map on the circle. Well, not multiplication by 2, squaring. And the induced map is multiplication by 2 on the integers. Okay. All right. I have just a couple more things I want to say about these induced maps. So some properties. So two properties. So the first one is that so the first one's about composition. So suppose you have x goes to y to z by maps phi and psi. So then, well, you can look at the induced map. Well, let me draw a diagram. So you have induced maps here, pi 1 of x, pi 1 of y to pi 1 of z. You have phi star, an induced map, psi star, and then you have the composition induces a map, psi compose phi star. And the claim is that this diagram commutes, which is to say that psi compose phi star is psi star compose phi star. Okay, so let's think about why this is true. Right, so phi compose psi star, how does this evaluate on some loop F? Some element in the fundamental group of X. So this is, by definition, phi or psi compose phi compose F. But now we see that, well, right, we can rewrite this as psi compose phi compose F. And that describes this as a composition of the induced maps. Okay, so all we used here is that composition of functions is associative. Okay. And then the other property of the induced map is that if phi is the identity map on X, then phi star, well, so let's just look at the definition. we're just composing with the identity, which does nothing. So phi star is also the identity. But now the identity homomorphism from the fundamental group of X to itself. Okay, so as a corollary of this, so together these two properties, how induced maps behave with composition and the induced map of the identity being the identity, these two properties fall under what is often called functoriality. And I think I don't really want to say anything about that right now. But maybe later. Okay, so the corollary I want to explain is that, so as a consequence of these two properties, we can see that pi1, the fundamental group, is a topological invariant. So remember, one of the goals of the course is to find topological invariants, properties of spaces that only depend, that don't change for topologically equivalent spaces. So that is to say, X topologically equivalent to Y implies pi1 of X is isomorphic to pi1 of Y. So proof, if X is topologically equivalent to Y, then there exist maps between them. Let's call them phi and psi, so that psi composed with phi is the identity of X, and phi composed with psi is the identity of Y. So then this implies that psi star composed with phi star, which is psi composed phi star, is the identity of X star, which is the identity of pi1 of X. And similarly, the other way around, phi star composed psi star, this is the identity of pi1 of Y. So this means together that phi star from pi1 of X to pi1 of Y is an isomorphism. Right, so together these two tell you that phi star is both injective and surjective. And that's exactly what we wanted.